Okay, so we're about ready to start. My name is Pantelis Antoniou. I work for a company called Konsulko, and I'm going to talk about transactional device tree and overlays. And it's a way to make reconfigurable hardware work. But I'm also going to talk about the story behind all this, because usually when you start working on something, you don't end up like this. Your goals are much more modest, but then you get expanded until you get something complicated like this thing. So device tree is all about describing hardware. So as you know, systems aren't getting any simpler, just getting more complex. And ARM-based systems especially are even more complex than that, because ARM started the trend of describing everything, including the clock tree, in the device tree. And that actually made the problem even worse. It wasn't like that, but eventually the clock tree had to be described in order to get power management work, and just roll down from there. I don't know how many of you have ever written something about a board file. How many of you know what a board file is? How many of you have actually written a board file? So quite a lot. So it's a familiar thing. You know, most people can actually write a board file. The thing is, the board file is not very scalable. If the platform is really complicated, it gets to be quite complex, and it's a wild west. Everything goes in a board file. People just keep on hacking stuff, poking registers, and it's really hard to use that as a base for your own designs. So for that reason, we have device tree. It's not a new technologies. I think we were talking with a guy yesterday, and he said he remembers when they started talking about it, and it was almost 20 years ago. But it started on PowerPC, but now almost every architecture uses it, besides x86. Well, actually x86 does use it, but it only uses it for a very special platform, which is, I think it's some kind of a DVR platform. But it is there, even there. So when we talk about device tree, what are we talking about? We have the Bible of device tree, which is a document called ePaper, and it says, describe system hardware. And I quote, device tree is a data structure for describing hardware, rather than hard coding every detail of the device into the operating system. You describe everything in a device tree file, which has a tree structure, and the standard especially states that describes information that can be dynamically determined by running software. What this means is, when you have an ARM SoC, the hardware configuration is fixed. You just need to pass that data to the kernel to make it work. But that's not exactly correct. So it's died out right now, but a few years back, there was quite a lot of complaints about device tree, and some of the complaints are quite valid. So I got some really interesting emails. That's a quote from an email I got Monday morning. It was a great day to start the day. So for some reason, it inflames people. I don't understand why. If you take a look at the code, it's just a few thousand lines of code. It's not that complicated, but it seems like it hit a nerve about how people that actually work on hardware think about working with it. If you try to impose some kind of structure to what they do, they kind of take it personally and say, okay, that's not the way I used to work, and I don't like you, but whatever. Some of the complaints are actually valid. I don't know how many of you have written a device tree definition for a device. So you know all about the language that's used. It's TTS file, and it's a little bit cryptic. It's not exactly a language. It's a declarative way to state facts and connections between entities. It's completely data-driven, so some of the hacks that we used to do when we used platform data doesn't work. One common thing that used to be done was that you had platform data, and then you had a function pointer to be called by the driver to do stuff whenever some driver-specific event happens. But since device tree is completely data-driven, there's no way to do that. So in order to get that to work, you need to do stuff like have some subsystems and then use subsystem services, and it's more complex. Another complaint is that there are completely no syntax checks at compile time. So if you have a driver that expects a property to be an integer and you pass a string, no error message. And you can't even figure it out at runtime because the property accessor actually will work, and it will pull the string data and present it as an integer. And it won't work, and you have no idea why. And since it's used to boot the system, you might make a mistake really for something that the system needs to boot, so you won't get any warning whatsoever. Just get something that doesn't work. But the thing that actually made me work with that stuff, the device tree, dynamic device tree, is that not exactly every hardware piece can be described at runtime. So you have things that you have way to figure out what kind of hardware is connected, but it's not static. You need to perform some kind of action, figure out what you have connected there, and then do something else to get it to work. So all this started on the BeagleBone. I don't know how many of you have a BeagleBone here. So there was another guy in a session yesterday, and he asked about people that have Arduinos. And this conference, more people have BeagleBones than Arduinos. I think it's a Linux conference. It makes sense. So the BeagleBone is a very low cost, $50. I don't know how much is it right now. It's 45. 55. I think the new. Yeah, the new version is more expensive. Yeah, so that's just because they need to run Debian on there. So more expensive. So the BeagleBone is a very low-cost, community-supported development platform for developers and hobbyists. It's quite simple by the standards of today, but actually it's very complicated compared to what used to be the normal a few years ago. So it's got a single core CPU. It's got quite a lot of memory, so that's quite good. Quite a lot of standard interfaces. But what really makes it important is that there is a way to build your own hardware devices, plug them in a 2x46-pin connector, and have them do stuff. I don't know how many were at the keynote yesterday with Andrew, and he used the BeagleBone for all his autopilot work. And he used it because it's actually designed for that kind of stuff. It's not just a board for running Python or something. It's a board that you can use to build other stuff that interface with real world. And the way that you do that is by capes. So capes, everyone has a different name. So you have Arduino has shields, BeagleBone has capes, the Mino board has lures. Maybe we need to standardize on a name. So when they started making the BeagleBone was right at the time where the big transition to device tree was made. So there was a choice to be made whether they would just keep on using the old 3.8 kernel that used board files, or we should just move to device tree. So If they use the board file, things would work easier, and maybe our lives would be easier as well, because when we started using device tree, a lot of problems happened. The biggest was that all the drivers were not device tree ready, but eventually that became better. But the big problem were the capes. The capes are actually identified at runtime. There is an I2C EEPROM on each cape, or used to be. I think I heard that the new capes do not use that. I don't know, maybe for cost reasons. You can still solder an EEPROM, I think. And the biggest problem is that you cannot support this scheme with device tree. In order to support that, there were some ideas about doing all that stuff in the bootloader. But if you come to think of it, it's a combinatorial explosion problem. So if you have 10 capes, and each of them can be stacked, and so you can have 4 capes connected, you must have either the bootloader build the device tree at boot time, which is, it's not a nice thing to do in a bootloader. Or you should have all the possible combinations of device trees for the capes connected available, and that makes it impossible because it's a few thousand. So the way to do that is to have a way to dynamically alter the live device tree whenever a cape is detected. And that's the pretty naive way that we started thinking about it. So, as I said, we started about the BeagleBone, but it's not actually the biggest use case. The biggest use case is other stuff like FPGAs. FPGAs are by definition dynamic, and depending on the kind of bit file that you load in a FPGA, a different hardware device is supposed to be created. And you need to do that on runtime because FPGAs now are reconfigurable. So there's no way to, it's not a good way to use an FPGA if you just, there are use cases where it's statically configured, but there are ways to use it when it's dynamically configured. Then there is a view that hardware is static, but I don't know how many of you know about the Project Ara stuff. So how static is that? It's everything is dynamic. So they created a whole new interconnect, new protocol, but yeah, maybe it's a little bit of an overkill. Maybe people can use the same architecture for something that's more easily created, because I think they have a lot of problems in getting that to the market. And then finally, we have a lot of maker types now that want to build stuff, and right now they use Arduino. Arduino is okay, but it's very simple to use, but it's not really, you can't do anything really impressive with it. You can toggle a few IOs, you can do some really cool stuff, but your role is going to be limited by that AVR and the programming model that you use. But if you ask for an Arduino person to write a kernel driver just for a LED, he's going to be out of his mind, and he's going to be right. It's just too complicated. Device tree and device driver writing is something for professionals. So we need to make it more simple. So we started in October of 2012 with the first patch, and it was a bus, cape bus. It worked, but it was a bad idea. All the comments in the review was that it's not a bus. You're not using a bus. It's something different. So you need to rethink things. So it didn't went well. So back to the drawing board, and we had to come up with something more interesting. So that's when we figured out that there is something in the kernel for many years. It's been there for at least 6 or 7. It's called, it's an option called config of dynamic, and it allows modification of the live device tree at runtime. It wasn't really used. It was only used for corner cases for Big Iron from IBM. But they needed that, so it ended up in the kernel. But it's something that we want to do. We can use it, but it's not complete. So the biggest problem is that it uses the destructive editing of live tree. After you made the change, it was set, and then you couldn't back it out. Now, it's not a big problem if you just need to change a few properties, but if you have to insert a whole the definition of a new peripheral, that's about, I don't know, could be 50 or 60 properties. So if you have to do that by code, that's very complicated, and then you would have to make sure that if an error occurred, then you had to back it out, all that out. So that was a big problem. The other problem is that all that editing was just on the live device tree, and they didn't affect the operation of the kernel. So let's say you modify the status property of a disabled node and make it enabled. That doesn't mean that the device would be created. It would just stay there in the live tree, and you had to use a different method to make the node to lead to the creation of a device. So it was a start, but it wasn't enough. So now, I wasn't the only one working on that. Grant Likely was also working on that problem. The first thing he did was that he moved the device tree from proc to sys, and that means that he made the device nodes now kernel objects. So that started the ball rolling, and then we had to change this. There was another thing in the kernel that wasn't very used. It was there's something called off reconfig notifier, which means whenever you get a modification of the device tree, you get a notifier fired, and then you can do stuff with it. Since it wasn't used really much, the semantics were a little bit iffy, so we fixed that. Another use case for the dynamic device tree is device tree self-tests. In order to use the self-test up to a few months ago, you had to actually insert the self-test data into your device tree blob, and then put with it, and then make sure that everything works, which is quite complicated. So now the test case data are dynamically inserted. So I'm not very. It's not exactly right for me, because we used a kind of special method for that, but now it works on x86 as well. So that's why. All that stuff got in the mainline by 3.17. So now let's go to the hard parts. So let's say we have a way to insert a number of device tree properties and nodes to a running live tree. Is that enough to get things to work? Well, turns out it's not enough, because we have something called p handles, and it's a way where in the device tree you point to another point in the device tree which contains information about, for example, the interrupt node or pin maxing or whatever. So just inserting a freshly compiled device tree into a live tree, it doesn't work, because all the p handles are going to be wrong, and actually they will clash because they start from 1. So we have a very simple case here. So let's say we have a base tree called foo. How all that stuff ends up is that you have a property that references another node called foo, and If you take a look at the device tree blob, you will see that the bar property is filled with a cell which contains the value 1. And similarly, we have another node. Now, we want to insert the second device tree to the first, but we also want to make the QUX property point to the foo node that's contained in the first tree. So we must have a way to resolve on runtime p handles and assign new values to the p handles that are present in the device tree blob that we're trying to insert. So I don't know how many of you know about how linking works. It's a similar mechanism. And it's actually more similar to the old way that we used to do linking, where you had to go and patch the binary with a symbol. You're a compiler guy, so you know. So we must have a way to resolve p handles, and p handles are like pointers. So a p handle is just an integer, and they are assigned by the DTC compiler, and we need a way to patch the device tree compiler to support all that stuff. There is a patch already floating by. It's under review. It's actually on version 3 now. So it will probably get in, but not without a little bit more work. So one of the goals would be not to change the device tree blob format at all, because if you change the format, then you need to change all the ecosystem that uses it. So you need it to change every bootloader, every tool that actually modifies it. So there shouldn't be any changes to the device tree format. And so that's why I used the device tree to hold that information as extra nodes that are prefixed by underscores. And those nodes contain resolution data. We have a way to mark device tree file that's a plugin that controls generation of fix-ups and local fix-ups nodes. We're going to see that later. And the base tree can be compiled with a -add option. It will cause generation of a symbols node that contains information about all the labels that are present in the device tree. But you don't need that now, because you can even use overlays with a target that's not p handle, but you can use a path. So let's go and see what's going on. If you compile the foo DTS file, that's what's generated. You see that for the foo node, p handle properties are generated. And you also see that there's a symbols node that says, okay, so I have a p handle that's named foo, and it's pointing at the foo node. So now we compile the QUX DTS, and we see that the first property that was a local property is actually defined. It's 0, 1. But the QUX property that's pointing to the foo tree, it's filled with something that's easy to understand. That's not a valid p handle. But now you see some extra nodes. You have the fix-ups nodes, which says that you're going to need to perform a fix-up for foo, which is at the QUX property, and it's at the offset 0 in the property content. And you also need to perform local fix-up for the QUX property. So it's like an object file, but it's expressed like a device tree blob. So we need to have a resolver. The resolver it's not that complicated. You find the maximum device tree p handle value, you keep track of it. You adjust all the local key handles of the tree that you want to insert by that amount. And for each property in the fixups node, you locate the node it references in the live tree, and you perform the fixup. And that's it. So now you have a new device tree inserted, and all the P handles are now correct. So now we're at the point where the device tree is correct, but there's no reflection of that device tree state to the kernel's device model. So we have to do that. So we have something called change sets. It started as transactions, and it's quite similar. Since we need to apply a lot of changes to the device tree, it's really a bad idea to leave the device tree in an inconsistent state. So you have to have a way to apply everything at once, and if an error occurs, just back everything so that the device tree is back at the original state. But you also need that in case where the cape is removed, so that you can go back to the original state without any special handling. So the way that we do that is we have something called change sets. After the change set is applied, we fire notifiers so that users that want to know about the state of the device tree can be informed, and then we can revert the operation when we're done with it. So they are part of the main line as of 3.17. What's the internal kernel API? So we just issue of change set init. We perform changes to the device tree using those methods which are similar to the already present methods for modifying properties in the kernel. We lock the kernel, we apply the change set, we release the mutex, and then when we're done, we call revert, and that's it. We don't need to do anything else. It's quite simple compared to what you had to do if you had to do it manually. So after all this is just legwork to get where we want to be, which is use device tree overlays. So now we have a way to apply the changes to the device tree. We have a way to notify users of how the change is applied. And now we need to make the changes be reflected to the device tree model. So now when we change the status property from disabled to OK, you want that device to be created. So the whole idea is to have a low-level interface, so that because there are many users of that, it's not a user-facing API. It's an internal kernel interface. We have a user-facing API, a generic Config.fs-based manager for the BeagleBone and for generic platforms, but usually you shouldn't use that. You should use something that's specific to your platform, because your platform will have a probe method to detect what kind of hardware is detected and apply the correct overlay. But it's good enough for hardware hackers because you don't need to do anything. Just apply an overlay, remove it, make a change to the cape, and then do it again. So actually, after the 7th version, it got in. So now we're in the main line. So you can use that already. What's the format of the device tree overlay? It's a plugin, as we mentioned. There is a fragment definition. You can have multiple fragments of the overlay. You have a target or target path property. The target property targets p handle. When you have a target path property, you target a specific point in the device tree, and the overlay contains the overlay, what you want to change in the device tree. So what's the in-kernel API? You just get your device tree overlay blob in memory. There are different methods to do that. Usually you can use request firmware, or you can use the Config.fs manager uses binary Config.fs attributes. just get your blob in memory. You call offFTT unflatten tree. You call offResolve phandles to perform the resolution against the running tree. Another call to offOverlay create, and you just apply the overlay, and you get an ID, something like a file handle, file descriptor. That's what you keep around if you need to destroy the overlay. Now there is a complication there. If you apply overlapping overlays, let's say you apply them on the same location, you don't want to remove the overlay that was inserted first while the other was still applied. So you need to have a way to handle overlapping cases and disallow removal of overlapping overlays. So that's...
And is it taken care of in the kernel itself?
Yep. So you don't need to...
Is it taken care
yes,
of?
it is.
So if you remove something that's further down the stack, you will allow it or not allow it?
If they're not overlapping, it will allow it. But if they're applying changes to the same subtree, it won't be allowed.
Okay. And you just get an error?
Yep, it says you shouldn't do that.
Okay.
So all that is the internal API. Now I'm going to talk about the Configure manager. Configure is the new thing.
Just one other question. Is that dependency noted anywhere? Or do we have to keep track of that ourselves and whatever the bigger manager is?
No, you don't need to track anything.
The point is if there's an error because there is overlap, do we know which other dynamic patch ultimately has caused the problem?
Well, there's a log message that says you're overlapping with this overlay.
So there isn't like a file that specifically indicates who has something?
I will add that. There's some new stuff coming up.
So you can force it.
No, I know, but just
There's a new patch coming out that's... Now, what the problem is that this should be in sysfs, so you need to make the device tree overlay to be a K object, and then hang various properties there so that you can control that. But it's coming. So the Configure manager is not part of the main line yet. Patches are provided, but not in yet. I don't know if you've ever used Configure. You might have used it for gadget, USB gadget, because the configuration of it is by Configure. Anyway, you just create a directory, you copy your overlay to a file, and that's it. You don't need to do anything else. The patch is dependent on a binary Configure attribute patch, and I'm going to remove the request firmware method because I think this is more useful.
How would you remove it from not using that method?
No, it's the original patch contained two methods. So you could do this, or you could echo the name of a firmware file and use the in-kernel request firmware method to get the blob. But this is, yeah, I think this is better.
This is a very different use case, right?
well, it depends what you're doing. Yeah,
This use case is driven by scripts, user space.
right.
I still have quite a few reservations about this because this interface, you've got control of the whole platform. So there is security implications with it.
There's a patch about the security
There's
communication.
security issues though with a lot of interfaces like this, though, ultimately, though. So this isn't a new security problem.
No, but I'm going to be cautious about it.
Yeah, that's fair.
The other side is with the request firmware, that's far more interesting when you've got a driver that's able to figure out what the board is,
Of course.
and then request the correct thing.
Yeah.
And then either that file will be in user space,
But we're not-
or the kernel will know how to load it.
We're not talking about an either or thing. We're talking about an and, right? So it's a matter of whichever makes the most sense.
Does the one-way switch that was requested solve that security issue sufficiently?
I need to take a look at it. I think it probably does, but Pantelis and I are going to sit down.
Yep.
and do this stuff today.
So what's the status of the patches? Well, most of it is in. Changesets were included. Overlays are included. Config manager is under review. DTC patches are under review as well. And I'm going to add, there's an overlay syntax sugar patch floating, which makes writing a single overlay very much simpler. I don't know how many of you use DTSA files and you use the ampersand phandle method. So you make the overlay looking exactly like that. So it's much easier to understand. You don't need to the fragment and target and all those properties. It's just implicitly created.
It also means we can demand our vendors to give us DTSI files for all their parts up front. Because then we can just
That's a good
write
idea.
the overlay file ultimately at the very top of our board. So
Under
ask,
DTSI.
I'm just saying, I tell everyone, teach your hardware team how to write DTS files. Then they can talk to you in a language that's completely unambiguous. I know, that's what everybody says, but we can all move towards it. Linux taking over the world, that was never going to happen, right?
Okay, you're more optimistic than me.
I'm not saying it's likely or easy, I'm just saying it's something we can move towards.
Okay. If your vendor does that, let us know which vendor is that.
That's my whole point, right? The good vendors will do it and everyone else moves to it.
Because if they can do that, their vendor kernel tree must be pretty good.
Okay, so let's talk about some new stuff. Overlays, we can say that the overlay stuff is just the beginning of something that needs to be done, is to make a reconfigurable hardware work, and how do you continue that road. So we have something called now device tree variants. The original patch used quirks. So overlays is something to be used whenever the kernel has almost booted. But what happens if you want to use the same device tree blob to boot a number of related but not exactly similar boards, like the same board but different revision. So the way that we do it right now is you have different device tree blobs for its different revision. And while this works, it's quite a burden for a lot of reasons. One of the reasons is it's really hard to deploy this thing. So let's say you have a board that has 10 revisions, then you need to ship 10 different device tree blobs for its revision. And since not everyone has the same revision, it's really hard to figure out if you missed something in an old revision, and then the boards get out of sync. So you might get the latest revision board to work, but all the older ones not. And I came across this problem on the BeagleBone. There was the latest one is the BeagleBone Black, but the BeagleBone White is almost similar. But BeagleBone White device tree wasn't correct. Although you can do the right thing by using the TSI files and making sure that everything works, reality is that it's a burden. Then there's another thing. Using multiple device tree blobs is a big problem in some cases for manufacturing. Gunder Rock, I don't know if he's here. Well, you can share your example, why this is needed in your case.
Well, in our system, we have a whole bunch of variants, like configurations that are hard to manufacturing doesn't really like the idea of having to have different device for each file for each variant. That's one thing that needs to be But at the time of manufacturing, it is no carrier or switch. Now, this is one problem. You cannot use ACI because ACI is not that old either. Anybody ACI has that. ACI is a little bit better suited to that kind of problem because but it's not flexible enough to let us essentially have support for this supply at the time for the manufacturer. And actually, we just had a discussion internally that people want to lock down ACI completely at manufacturing and allow the manufacturer to think about buyers, tax buyers, getting them out of the home. Enable ACI updates to enable that possibility that something back is whole. So ACI is various how being left with other people's devices. You could try to use overlays, describing the base board, using the base device overlays, but that doesn't work well either because sometimes the overlays aren't hard, and that's what's running what's themselves. They have to be loaded. They have to be loaded to the period part. So all that makes it quite difficult to have multiple files. It's easier to single file than a file associated with the kernel. Now, ultimately, we're aware that studying all those issues that we used yesterday, but it is early, so yes, we're well aware that the advisory file is associated with the kernel. But at the same time, we come to tie it together, finding it in one file. So overall, we need something like Pantelis said, beers that don't smooth that we came up with that works for all things. Where actually mentioned the Pantelis says that it's not simple to accept it, we'll have to carry that message prior to
Okay.
It's kind of interesting to me that in advisory role, it's kind of considered in the other something like this, which is based on high role, so they are kind of having trouble dealing with things like overlays. It's accepted that you have provisions in the high tables that let you deal with varying hardware. So it's kind of
Thank you. So there's a patch RFC floating about, which is for the Bicklebone white and Bicklebone black. So you can boot the same device tree blob for both, and it will patch the device tree according to your booting device, and it will work. It just makes things easier for deployment, and it reduces the pain, and that's the idea behind it. So another idea is that since now we have a way to track pay handles and their reference targets, if you think about it in a high enough level, this is just a dependency graph. So there's an RFC patch that uses that information that we already have to make sure that the device probe order is correct. I don't know how many of you ever came across the way that sometimes a driver depends on another driver and it doesn't load because the other driver hasn't been probed yet, and the first driver has to be modified to work with eprobe defer, and yeah, it's a little bit of an issue. You can make it work, but it slows down boot, and it's just not really. If you can avoid it, it's better. So there's a patch that uses the p-handle references as a dependency information and rearranges the device tree probe order so that it's supposed to be correct. And in the meantime, it also detects dependency loops, which is bad, but it seems to work, but for now. And I think I'm going to continue that road to have a parallel device probe. So if you have an SoC that has something like 50 drivers, all of them are probed in order, and some of them are actually taking a lot of time to be ready. So if you could just do that in parallel, so you could say this is the system D of the kernel. So it's not ready yet, but I think I'm gonna finally do that at some point in the future. The idea is to reduce boot time. I know you shouldn't. It shouldn't matter so much because you can always use suspend resume, but suspend resume always has problems, and it's really tricky to get it working correctly. So.
The biggest problem you're going to run into with parallel device probe, we've tried it many times, is buggy drivers. The drivers that do the wrong thing. So when you tackle that, you'll need to be able to enable it selectively. Sorry, the biggest problem with parallel driver probe is not going to be the framework. It's going to be buggy drivers.
Yeah, but it's. I think it's going to be a per board option. I'm not crazy enough to enable it by default.
So that's the same way to go about it, is get it working on a particular board, be able to prove out all those drivers, handle it correctly, and then it could be a flag to enable it on additional boards. That would actually solve all the problems.
So that's the stuff that I've been working with, but there are other users. I don't know if you've seen the patches by Alan. It's an FPGA manager, and it actually is going to use device tree overlays as part of their framework to create the devices that are instantiated by the FPGA being loaded. And it just makes sense, just insert an overlay and everything would just work, including the programming of the FPGA. Eventually, I'm gonna finish up the BeagleBone Cape Manager that started everything. It's still not ready. That's 3 years and counting, but that's mainline for you, and whatever you come up with. So that's it for me. Thank you for listening. Any questions? Alison.